Yeah, I'll like to talk to you about something called bisection closed families, which is a fractional variant of a restricted intersecting set systems. Okay, and basically, if you have a collection of subsets of 1 to n, which satisfies the property that you take the intersection of any two, its size is half the size of this or that, then you say that the family is bisection closed. Okay, then here's here's one example of a bisection closed family. Okay, so you want half intersections, right? So let's say you take all the two element sets 1, 2, 1, 3 up to 1n. Clearly this together in itself is half intersecting, it's bisection closed. But you can also add the four element sets 1, 2, 3, 4, 1, 2, 5, 6 up to 1 to n minus 1n. Assume n is even for simplicity. Then a little bit of staring at it will convince you that this is also bisection closed in itself. And so we have produced a family with n minus 1 plus another n by 2 minus 1. So that's 3n by 2 minus 2 sets. Okay. Here's a very different construction which turns out to give the same bound. So you start with any Hadamard matrix, okay, and you form this block matrix H minus J, where J is the all ones matrix, okay, and you read every row as the 1 minus 1 incidence vector of some subset of 1 to 2m, if H is m cross m. Then you can exactly the Hadamard property, which says that the rows are pairwise orthogonal, will imply that these sets that you get, except after throwing away two of them, will be a bisection closed family. And so you have 3m minus 2 sets, subsets of 1 to 2m, that's again giving you the bound, 3n by 2 minus 2. So two very different constructions, both giving you the same bound. You have to ask, are these families extremal for the problem? And we don't know. In fact, we don't even know a linear upper bound. So you take any bisection closed family, the best we know is that you can do n log n for an upper bound of the size of f. And the conjecture is that there should be an absolute constant so that the size is bounded by Cn. All right. So I want to give two recent perspectives, one probabilistic, one sort of geometric. And to do that, we'll go via some linear algebra. So start with a bisection closed family over box n of size m. Take its 1 minus 1 incidence matrix and compute xx transpose. So the entries will depend on the various intersections of A and A complement with B and B complement, because that will count the ones and minus ones. But a little bit of algebra will show that it has something like this form. So it's n minus 2 times the size of A if A is the one sort of bisecting B, and it's n minus twice the size of B if B is the one bisecting A. And so let's simplify this. Just remove n from everywhere and divide by 2. So this is a symmetric matrix whose off-diagonal entries are either the size of A or size of B. Its rank is bounded above by the rank of xx transpose. That's, you get an n plus 1. And capital M is a little m cross little m matrix. So if you have a linear lower bound on the rank of M, you have a linear upper bound on the size of the family F. So let's generalize. Let F be any field. Pick any A1 to AM which are non-zero, and look at the class of all symmetric zero diagonal matrices whose ijth entries are either AI or AJ for all possible choices. Do all these matrices have a linear lower bound on their ranks? If we could answer this question, then we would have also got an answer to the original conjecture, right? So what we can do here is pick one at random and then see what happens. So to do that, we map these matrices to tournaments. So tournament is just an orientation of the edges of the complete graph. So given a tournament on 1 to m, if I beats j, then you create a matrix in which the ijth entry is ai. If j beats I, you create a matrix with the ijth entry aj, right? And you can go vice versa. Given a matrix, you can of course write on a tournament which it is defined by. So if you pick a tournament at random and you look at the associated matrix that you get, then we are able to show with high probability that its rank is at least m by 2. Right? And the reason being that if you flip any one edge of a tournament, then you're really touching only two entries, the ij and jith entry. So so that's useful. It's a useful observation for us to apply a concentration inequality over there. So that's the first thing I want to tell you about. This is a joint work with Niranjan Balachandran at IIT Bombay and Srimanto, who's at IIT Palakkad right now. So for the geometric picture, let's go back to the two families I showed you, the sunflower family and the Hadamard family, right? So in both cases, the sets which occurred there were only of two distinct sizes. So in the sunflower family, you just had sets of size 2 and 4. The Hadamard family, you had sets of sizes n by 2 and n by 4. So if you have only two distinct sizes, then a trivial upper bound on the size of the family is just 2n. You have n in each level. But these constructions are giving you 3n by 2, roughly. So can you somehow improve 2n to 3n by 2? this is in the linear algebraic language, can you give a better lower bound than the trivial bound of m by 2 on the rank of a matrix in that family where there are just two distinct entries, non-zero entries alpha and beta. Okay, so what we're able to show is that this depends on whether a certain bipartite graph that we can define in terms of this matrix has an eigenvalue with high multiplicity or not. So define mu to be this quantity such that it squares alpha beta by alpha minus beta the whole square. Then the rank of M is low if the associated bipartite graph has mu as an eigenvalue with high multiplicity. So the question then becomes, okay, where do I search for bipartite graphs with eigenvalues of high multiplicity? And you should look at symmetric designs, because if you have a 2vk lambda design, you know that its spectrum, I mean, you look at the point block incidence bipartite graph for a symmetric design, then it has spectrum which has an eigenvalue of high multiplicity. All right. So does this help us? Well, in a sense, it does, because you can use, let's say, the complete bipartite graph minus a matching, which you know how to compute its eigenvalues, to show that if you permit real matrices, then yes, you can go really close to m by 2. So this doesn't help us improve the trivial bound. So maybe not real, but you want, let's say, rational or integral matrices. Then also we can't do it, because there are things called Hadamard designs which have these parameters, and using them we are able to show that give me a threshold epsilon, I can get within half plus epsilon of the rank. So so really speaking, we are not able to improve the trivial bound. These are sort of our knowledge of symmetric designs is somewhat relevant over here. Other than the Hadamard designs and the complete bipartite graph, other symmetric designs that we have somehow do not give us matrices of low rank. So maybe some further conditions are important. And let's go back again to the Sunflower and Hadamard families. I'll just leave with this open problem. So there, not only do you have sets of two sizes, those sizes are in the ratio 1:2. So maybe if you impose that further condition on alpha and beta, then what can we say? The problem becomes finding bipartite graphs with root 2 as an eigenvalue with high multiplicity. So if you find some guy like this in the wild, please let me know. It'll be very interesting to me. And if you find out that no such guy can exist, that is also very interesting. Do let me know that as well.
Okay. Okay. So let's thank Bradish.